Hello guys, welcome back to another video. Now, in this video, we're going to be looking at projectile motion. Now, we're going to break this video up into 4 parts. The first part is going to be dealing with velocity, and the second part is going to be dealing with the time of flight. The third part is going to be dealing with peak height, and the fourth part is going to be dealing with range. And I expect that after watching this entire series, you should have mastered projectile motion. You should be a literal projectile ninja. Let's get into it. Now, the first thing we're going to be looking at, like I said, is velocity. In relation to what? To projectile motion. So what is a projectile? Look at this over here, this green chalk. And look at what I'm about to do right now. Look at this. If you saw what I just did, I threw the chalk. That action of throwing it, that action of ejecting it is called projection. That is what we call the projection action. Now, this thing which has been projected is what we call the projectile. So a projectile is just an object that has been launched, and then when it has been launched, it traces a path in the air, which might be a parabola or half of the parabola or a semi-parabola. This is the path which our projectile takes when it has been launched into the air. So I repeat, a projectile is nothing more than the object which has been thrown or ejected or launched from off a certain point and follows this path in the air. So in most cases, our projectile usually follows the path of a parabola unless it has been launched vertically upwards. In this case, it just follows this linear motion or this linear path. It goes from this point up to a certain peak point and then comes back. And this path followed by our projectile, we call the trajectory. If you've ever heard the name trajectory, this is what it's referring to. It's simply the path followed by the projectile. Thus, our object which has been launched from a certain point, say with a velocity v at an angle of theta to the what? To the horizontal. It might not be to the horizontal, it might be to the vertical, depending on where you choose to place your angle. Now, let's look at velocity. So when it comes to projectile motion in physics, what we usually do is break up the motion into 2 parts. The first part being the vertical aspect of the motion, and the second part being the horizontal aspect of the motion. So say your projectile follows this path. This path. How we approach this motion is by doing this. We break this motion into first the vertical aspect of the motion and then the horizontal aspect of the motion. You'll get to understand what I really mean by this later when I delve a bit deep into this entire idea. Now, let's say our object has been launched from off this point here, and it has been launched with a velocity v, and this angle over here with the horizontal is theta. This is how we approach projectile motion calculations. Remember, we have the equations of motion. Let me use a different color. We have the equations of motion. V is equal to u plus at, and please memorize these equations. Like, I know a lot of people do not age cramming or memorizing, but if there's anything you have to get used to, anything that has to be at your fingertips, it's these equations. Know them inside of your sleep. Memorize these equations. V is equal to u plus at, and we've got v squared is equal to u squared plus 2af, and we've got s is equal to ut plus half at squared. Now these are the equations of motion you're going use them when you're dealing with projectile motion. You do not need any other equation, trust me. You only need these three. Any other equation can be derived from this three. That is any other equation required in projectile motion, or the projectile motion problems you'll be facing in your tests, in your exams, or in your homework problems. Now, when we are dealing with velocity in projectile motion, we do not use it in its raw form. That is, we do not take it as it is right here. What we do, like I said, we break up this velocity into the vertical component, or the vertical aspect of the motion, and the horizontal component. Those two, that is what we get after we decompose this or break this into parts, is what we use in the equations of motion. We do not take this velocity as it is. I repeat, drill this into your head. We do not take this velocity as it is. Say you were given this velocity as 50 meters per second at an angle of, say, 30 degrees to the what? To the horizontal. Say this is the velocity you're given here. We do not take this and substitute it into this or this or this or this or that. We do not do that. We break this into components. That is, the components are what we use in the equations of motion. We do not use this velocity in its raw form. I'm going to show you how to break up the velocity into its constituent components, and how we apply those components into the equations of motion so that we get whatever values we're looking for. Okay, so looking at this case, say you are given a projectile or an object that has been launched from the ground at an angle theta with a velocity of v, and traces this trajectory up to a certain point. Let's say at a point that is at the same level as this. Let's say this is what you're given. Now, what is our aim? What we want to do here is learn how to use this velocity in equations of motion. But like I said, we do not take it as it is. We break it down into its constituent components. That is what we want to learn here right now. So how do we do that? How do we get the vertical component of this velocity, and how do we get the horizontal component of the velocity? This is what we do, guys. Pay attention. What we do is simply use the concepts of simple trigonometry. That is, those concepts you learned as that is opposite over adjacent, opposite over hypotenuse, adjacent over hypotenuse. This being cos, sine, and tan. The concepts around this mnemonic, if you will, are what we use in order to get the constituent components of the velocity. Now, let's see exactly how to do this. We want the vertical component of the velocity, which would be a velocity in this line. And we want the horizontal component of the velocity, which would be a velocity in this line. That is the horizontal line. And we've got an angle of what? We've got an angle of theta. Let's do this. We've got an angle of theta. We can label the horizontal component in the x direction, or in the horizontal direction, as Vx. And we can label the vertical component, that is the component of the velocity in the y direction, or the vertical direction, as Vy. Now, let's take this line and join it with this part, so that it makes a bit of sense. Let's do this. So what we want here is Vx and Vy. Those two are the components of this velocity. They are the constituent components of this velocity, which we can use in the equations of motion to get whatever values or whatever variables we're looking for. Now, like I said, to do this, we simply use simple trigonometry. But how exactly? Picture this velocity. That is the velocity you're given, this raw velocity. Picture it as the hypotenuse triangle. That is the hypotenuse of a right-angled triangle. Once you do this, you can simply extend this and picture this as the adjacent and translate this part over here onto this side. So basically what you want now, you want Vx and Vy. Now our aim is to get the values of Vx and the values of Vy. Why, guys? So that we can use them in the equations of motion. Now, how do we get, for example, Vy? Vy. How do we get Vy? Remember, this is nothing more than a triangle. The moment you picture this as a triangle, a right-angle triangle, things become very simple. Now, remember, I previously gave an example of the velocity which you could be given for this. And I say, let's say we've got 50 meters per second. This is per second. Or let me simply use this. 50 meters per second. And this angle could be, say, 30 degrees. So say the velocity you're given, that is this V over here, is 50 meters per second at an angle of 30 degrees to the horizontal. What you then have is this. Remember, 50 meters per second is being represented by the length of this arrow or the length of this segment. What we do then is bring this 50 and put it over here. It's the same as putting it over here, but since I've drawn this triangle on a separate area, it becomes a bit more clear. So we've got 50 meters per second here. I'm not going to write the units. And then we've got an angle of what? 30 degrees. 30 degrees being this theta, guys. So we've got 30 degrees here. And then we've got Vx. And then we've got Vy. But the variables Vy and Vx might intimidate some people. So let's change them and simply put something more familiar. Let's put an A here and let's put a B here. But always bear in mind that our A is representing Vy and our B is representing Vx. So how do we find, for example, first, how do we find Vy? That is thus. That is A. How do we find our A? We simply use, like I said, the mnemonic, if you will, Chasho, Tau, or Sokato, or whatever works for you. Now, what are we looking for here? We are looking for the opposite. Remember, A is opposite the angle 30 degrees. So we're looking for the opposite. So if we're looking for the opposite, we come here and look at what exactly is associated with the opposite. We've got Shou here and we've got Tau here. But because we do not have the adjacent, we're not going for this. We're going for this since we have the hypotenuse. So we're going to use this. Sine is equals to opposite over hypotenuse. So we've got sine 30 degrees is equal to what? Is equal to the opposite A over the hypotenuse of 50. If you make A the subroot of the formula, by simply multiplying both sides by 50, you get A is equal to 50 sine 30 degrees. This is your value for Vy. So let's write that. Remember we said Vy is equal to A. So this is your value for Vy. 50 sine 30 degrees. But let's not use that here. Since we gave this as an example, we want to write this in the most general form possible. So we can write this as V sine theta. V being our magnitude and theta being our angle. That is the angle we're given. So the way we compute Vy, given theta over here, close to the horizontal, and the magnitude, in general, is by substituting V here and theta here. So we've got Vy is equals to V sine theta. Now, what is Vx? Now, I'm not going to work out the math for Vx, but what we simply have here is the adjacent B, which is Vx, and the hypotenuse 50. So we come here and we look for the adjacent and the hypotenuse, and we see that it's associated with cos. Again, we're not using tan. Why? Because now we can use tan since we have the value, but we're not going to do that. We're going to put it aside and use this adjacent and the hypotenuse associated with cos. So what we have in this case is cos 30 degrees is equal to what? Is equal to B over the what? Over the hypotenuse of 50. And if you multiply both sides by 50, you get B is equal to 50 cos 30 degrees. Now, because we get 50 cos 30 degrees, we now want to write it in the most general way possible, like we did here. What we get then is V cos theta. V representing what? The 50, and theta representing what? The 30. But if you're given, say, an angle of 75, now you can substitute it here, and say a magnitude of 20, you can substitute it here. Now, this is how we get the constituent components that make up our velocity, V with a cap on top here, or with a line segment on top. These are the velocities. Now, by the way, these are not just components, these are actually velocities, but they are velocities associated with the horizontal direction and the vertical direction. That is, the vertical direction and the horizontal direction respectively. Now, this is what you use in the equations of motion. These two, or these two, these are what you use. These are the velocities you use in the equations of motion. You do not take this in its raw form. That is to say, you never substitute 50 or the 30 degrees in your equations of motion. You substitute this. That is, if it's in this case, you substitute 50 sine 30 and 50 cos 30. You never substitute the 50 meters per second or the 30 degrees in any way. So, hence it is important to know how to decompose a velocity into its constituent components so that you're able to use them in the equations of motion. So now we can do that. But before we proceed, before I show you other aspects of the velocity or other things behind the velocity you have to know, I want to show you a simple shortcut or a simple way of computing the velocity or the constituent velocity Vy and the constituent velocity Vx without going through the trouble of drawing a right angle triangle and bringing into mind the mnemonic Churchill Tower or SOHCAHTOA or whatever you've crammed or memorized into your head. This is how we do this. So the way we get these components quickly without drawing the right angled triangle is simply by using this trick. I'll label it with a star here. The trick says cos, let's use a different color, cos the side close or adjacent to the angle and sine the remainder. This this is our trick here. Now I just coined this statement right now. I've never used this statement ever. I use it in my head. Like, I do not literally say it out loud, but I just use it implicitly in my head. Now, the trick is cos the side close to the angle and sine the remainder. What am I saying by this? Let's say you're given the angle theta and you're not given the angle alpha. How you use this trick in order to find these components, that is the components of the velocity you're given. Remember, the trick says cos the side close to the angle. Which is the side close to the angle? Now, if you are given an angle theta, the side adjacent or close to the angle is Vx. This is not close to the angle theta. This Vx is close to the angle theta, not the side Vy. The side Vx is close to the angle theta, hence why we call it the adjacent. In this case, this would be the adjacent. So Vx is close or right next to the angle theta. So this is the side that takes the cos. Hence we have V cos theta, V being the magnitude of the velocity you're given. And what does it say in the remaining part? Sine the remainder. That is the remaining side. The remaining side is Vy. So we sine the remainder. If you come here, we've got sine theta. We're still using our angle theta. Sine theta, so it's V. That is the magnitude of the velocity, sine theta. In the event that you are given, the angle alpha, but you were not given the angle theta, our rule still applies. Cos the side close to the angle. Which side will be close to the angle in this case now? The side close to the angle will then be what? Vy. Remember, this and this is the same thing. The side close to the angle would then be Vy. And what happens to Vy? What happens to Vy? Because Vy is close to the angle, we would have V, that is the magnitude of this velocity, cos alpha. Why? Because in this case the angle we are given is close to the vertical or close to Vy. And what happens to Vx? Vx is not close to this angle. Vx is what? Because this is the remainder now. Vx is sine. So we go V sine what? Alpha. So if you were given this angle and you are not given theta, that is, you are not given this angle here, these would be the values you'd get for Vy and Vx. But in the event that you are given theta, these would be the values you would get for Vy and Vx. And if you punch on your calculator, you'll find that V sine theta is equal to V cos alpha, and V cos theta is equal to V sine alpha. How do you verify that? Now, let's say your alpha is, say, 30 degrees, and your V is, say, 50. So let's say your alpha, okay, so I don't want to confuse it. Let's say it's 25 degrees. I don't want to confuse you. You might be thinking about the previous 30 degrees. Let's say it's 25 degrees. Let's say your alpha is 25 degrees. What then happens is this, and your V is 50. I want you to punch in your calculator. If you put 50 here and you put 25 degrees here, you've got 50 cos 25 degrees. You will find that 50 cos 25 degrees is equal to what? Now, say 90 minus 25 degrees. If you say 90 minus 25 degrees, I believe we get 65 degrees. Now, say V, that is 50 sine 65 degrees. If you say 50 sine 65 degrees, you find that is equal to you find that is equal to 50 cos 25 degrees. The same applies to this case. If you say 50 sine 25 degrees, you find that it's equal to 50 cos 65 degrees. So this over here and these are the the same, this and this are the same. It all depends on the angle you're given. That is where the angle is situated. But this is the trick if you want to find these components first. If you do not want to use the right-handed triangle and the Projectile mnemonic, if you want to do things quickly inside your test, inside your exam, simply cram this or memorize this. It might come in handy. So this is how we find the constituent components of the velocity we're given. And like I said, these guys, these little funny looking things are what you use in your equations of motion. You do not use this capped V or this V with a line segment of top on top, or the raw velocity in your equations of motion. You use the components that make up this velocity in your equations of motion. So like I said, Vy is associated with the vertical, Vx is associated with the horizontal. The same applies for this. Vy is associated with the vertical and Vx is associated with the horizontal. This being equal to this and this being equal to this. Now at the end of our video series, we're going to be looking at problem sets or practice problems. We're going to be looking at problems and actually solving them using numerical values and not using this V and thetas and the alphas and so forth. We're going to actually look at real numerical values. We're going to be playing with the real angles and real values and real questions that might show up in the exam. The problem sets and the practice questions and all that are reserved at the end of the series. When we have looked at velocity, when we have looked at time of flight, when we have looked at peak height, and when we have looked at range. After we've covered those topics and understood them, only then can we begin playing with the practice problems and the problem sets. Why? Because I do not want you to memorize how we solve certain problems. I want you to understand the concepts first. Once you understand the concepts, only then can you begin to try to tackle the problem sets or the practice problems. Now, I want to show you something else that will be very, very handy when it comes to attacking projectile motion problems with regards to velocity. Now, I want you to pay close attention, guys, because the information I'm about to give you is very, very crucial. It's very, very important when it comes to solving projectile motion problems. Now, imagine an object is projected from off this point and then traces this parabola or this entire path and lands at this point. Now, this is what I want you to drill into your head. This point, say, when it lands, the point at which it lands is at the same level with the point at which it was initially launched. Say these two are at the same level or same height, if you will. That is point A and point B are at the same height. Bear this in mind as I speak. Now what happens is, one of the most interesting ideas or things about projectile motion is this. Remember I said this velocity, when it comes to dealing with calculations, is broken down into its constituent components or the component velocities. Let me use a different color for this so that I do not clutter everything. Let me use the color green. So let's say this is the vertical component of the velocity, and let's say this is the horizontal component of the velocity. What happens is this. The moment our projectile reaches this point, it has a different velocity, different from this, what we began with. Let's label this as V1. V1. When it reaches this point, it now has velocity V2, which is in which direction? This direction. And this velocity 2 can be broken up into its constituent components. We've got a V there, and we've got a V there. And when it reaches this point, Again, it has a certain velocity, which we'll call v3. And when it reaches this point, again, it has a certain velocity, directed in which direction? This direction. And again, this can be broken down into its constituent components. And then when we reach this final point here, again, it has a certain velocity. Let me put b over here. Let me write b over here. It has this velocity. And these two can be broken down into its constituent components. Now, I'm not saying, guys, please, I'm not saying that it doesn't have a velocity when it reaches this point, it doesn't have a velocity when it reaches this point, or this point, or this point, or this one. No, I'm not saying that. But I can't draw all the velocities associated with these points in space. I can only draw a finite number of velocities. Now, so I chose this velocities, or these points in space. Okay, for this point, we again have, let me draw this as this. For this point, again, this velocity over here can be broken down into its constituent components. But however, at this point, as you will see, I'll explain later, we've got a vertical component of 0. That's why I'm not putting any arrow here. Now, what happens, guys? Please drill this information into your head. Like I said, it's very, very important. What happens is this. Let me use a different color again. What happens is this. When the object is launched, it's launched with a velocity of what? Sorry, I didn't label this. This is v4, and this is v, let's say 5. What happens is, when the object is launched, it's launched with a velocity of, say, v1, which I said can be broken down into its constituent components. Now, the interesting thing here, guys, is this. This horizontal component, which we found, or which we find in this case, to be what? To be v cos theta, using that trick, guys. V cos theta. The horizontal component at this initial launch point is the same as the horizontal component at this point. V cos theta. And again is the same as the horizontal component at this point. V cos theta. The theta being this angle, guys. And again, at this point, the horizontal component remains the same. It doesn't change. The V being the magnitude of this. Let's call it V1 since I now put V1 over here. The magnitude. The magnitude of this initial velocity. So, when we reach this point, again, we have the same value for the horizontal component. V1 cos theta. And again, when we reach this final point, it doesn't change. We still have the same value for the horizontal component, which is what? V1 cos theta. I hope you can see that. So this is very, 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 very important, guys. The horizontal component of the velocity doesn't change throughout the journey, no matter at which point our object lands. If it landed at this point, it would be fine. If it landed, say, at a certain point way below this level, it would still be V1 cos theta. The horizontal component of the velocity doesn't change. to such an extent that you can simply use the speed is equal to distance over time formula when you're working with this aspect of the motion. Say you're given the velocity, that is the horizontal component of the velocity, v1 cos theta, and you're given the distance, which we usually call the range, that is the distance from this point up to this point, on the same level in this case. So you're given the distance, you're given the speed and the distance, and you want to find the time. The time would then simply be the distance you're given over what? V1 cos theta. Bear this in mind, guys. The horizontal component of the velocity does not change. And this t, by the way, would be called the time of flight if you use the range. It would only be called the time of flight if the d you're using is the horizontal displacement associated with the entire journey. But we'll cover that later. So the concept or the idea I want you to drill into your head is that the horizontal component of the velocity doesn't change. Now, let's look at the vertical component of the velocity. Now, the horizontal component of the velocity is v1 cos theta. What is the vertical? Using the method we used previously. Let me use a different color again. Okay, let me pick this. What would be the vertical component of the velocity? This velocity. The vertical component would be v1, v1 being the magnitude. I hope you know how to find the magnitude of this, guys. If you don't, let me know in the comments and I might make a video on that. V1 sine theta. This is our vertical component, or this is the vertical component of this velocity. Now remember, I just mentioned that throughout the entire journey, no matter the shape of the trajectory you're given, that is, no matter the shape of this path, whether your object has been launched from off a cliff or whatever height, it will always have the same value for the horizontal component of the velocity. Remember, I just mentioned this. But now, when it comes to the vertical component of the velocity, please do not expect that you will find v1 sine theta at this point. We do not have v1 sine theta at this point. We do not have v1 sine theta at this point. We do not have v1 sine theta at this point, and we do not have v1 sine theta at this point. With the vertical aspect of the motion, the vertical component varies. That's why I said at this point it's zero. As the object rises due to the influence of gravity, the vertical component of the velocity begins to decrease up to the point at which it reaches a value of zero. And then once it reaches a value of zero, and the object begins to descend, again the force of gravity is still acting, so it accelerates the object now. That's why you begin to see components when we are now descending. So with the vertical direction, we do not have a constant value throughout. It varies. So do not try to memorize anything in regards to the vertical direction. But with the horizontal direction, it remains the same. This is just how it is with projectile motion. Another important piece of information I want to tell you guys, and I believe this is the last piece of information I'm giving you with regards to velocity in relation to projectile motion. Now, another piece of important information is this. Remember, I just told you about all those funny ideas. Now, they are funny ideas, yes, but they are true. Now, another important piece of information is this. Whenever you're looking at the trajectory of a projectile, and you take 2 points at the same level, say this point and this point, 2 points at the same level or 2 points at the same height, what you get is this. Not only is the horizontal component of the velocity the same at these 2 points, but what also happens is this. The magnitude the magnitude of the velocities at these points that are at the same level are the same. I repeat, the magnitudes of these raw velocities are the same at these same points. Again, say this is at the same point as this. I know this is not at the same point as this if we're looking at it, but let's say they are at the same point. What am I saying? I'm saying at this point we've got a velocity of v2, at this point we've got a velocity of v4. Now, the magnitude of this velocity v2 here would be labeled v2, and the magnitude of this velocity here would be labeled v4. Just like I was labeling the magnitude of this velocity here as v1. What I am saying, guys, is if this point was at the same level with this point, this magnitude of v2 would be equal to this magnitude of v4. That is their magnitudes, guys. The magnitudes. Let me use this to make it a bit strict. The magnitudes would be equal, guys, if these 2 points were at the same level. The same applies at this point here, which is at the same level, say, with this point here. The velocity associated with this point has the same magnitude as the velocity associated with this point. So, for example, going back to our case here, if at this point the velocity has a magnitude of, say, 10, then what I'm saying, if v2 is equal to 10, v4, which is at the same level with this, is also equal to 10, guys. That is what I'm saying. So, if our object is launched, say, from the ground with an initial velocity of this, and then lands at our point B, that is at the same level as the launch point, what happens is this. The magnitude of this velocity, which we shall denote as simply being v1, is equal to the magnitude of this velocity, which we shall denote as v5. What we're denoting as v5 is the magnitude of this velocity, guys. It's important. I'm representing the velocity with this here, but I'm representing the magnitude of this with this without the arrow. Some people prefer to represent the magnitude of this as this. I don't know if you have seen this, the magnitude of this as this, but I'm simply representing it with the letter only and the subscript. So, what I'm saying, guys, is this. The magnitude of this velocity is equal to the magnitude of this velocity. But this only applies, and I repeat, it only applies for points at the same level, guys. Points at the same level or at the same height, if you will. At any level, for any trajectory you are given in projectile motion, if you are given, say, a cliff, and a projectile was launched from this point and it took this path, this would only apply for points at this level. Why? Because if you go at this level, you do not have an associated point here, since our object has been launched from this point. So, it applies to all trajectories, but be careful how you apply the idea. You have to use a bit of common sense, like in this case. You have to know that it only applies at this upper portion of the curve or the trajectory. And again, another important piece of information. Okay, this is the last one, guys. This is definitely the last one. Another important piece of information, and it's similar to what I just told you. Again, it applies to points at the same level. The information is this. For points at the same level, the angles associated with the velocities are equal. Granted, we're looking at the same axis. Say we're looking at the angles associated with this horizontal axis, or the angles close to the horizontal axis. Now, in this scenario, our object has been launched with this velocity at an angle theta. Now, we know that this point is at the same level with this point. What I'm saying is this. Our object has been launched at an angle theta. If you come this side, and you want to determine this angle adjacent to the horizontal, let's call it beta. If you want to determine this angle, know that this angle is simply equal to theta. That is, it's simply equal to the angle at which this velocity makes with the horizontal. Now, if you were given an angle here of, say, alpha, this angle adjacent to the vertical too would be equal to alpha. Again, the same applies in this case. Say this is angle, angle what? Now I'm running out of angles. Let's say this was angle omega. And this point is at the same level with this point. But because this angle is in relation or adjacent to the horizontal, the angle is equal to here will also be adjacent to the horizontal. So this angle and this angle are equal. Granted, this point is at the same level with this point. If these 2 points were at different levels, it wouldn't apply. So what have we seen here? We've seen that for points at the same level, we've got angles being equal, we've got the magnitudes of the velocities being equal, and we've got the horizontal components of those velocities being equal. This applies always and for any trajectory you're given. We're going to be utilizing all those tricks in our problem says, that is the questions or the problems we're going to be tackling after we've covered the entire series related to projectile motion. So that is it, guys. Thank you, guys, if you made it to the end. Thank you if you made it to the middle. Thank you if you covered 25% of the video. Thank you if you covered, say, 10%. And thank you if you only watched a second. Please leave a like, subscribe, and comment if you enjoyed the video. See you in the next one.